Okay, so we're moving on to talk about the chi-squared test for goodness of fit here. Um, get my laser pointer. There we go. All right. So we talked about using chi-squared as a test statistic for a hypothesis test regarding a variance or standard deviation. There's a couple other cases we can also use the chi-squared test for. Comparing a frequency distribution that from an experiment with what is a theoretical distribution that we might expect, and assessing whether two traits or characteristics in a population are associated, and that's what we'll cover in the section after this one. Um, so we're concentrating mostly on this first one. Well, not mostly, entirely on this first one in this video. Uh, the additional caveat for this is that the experiment must satisfy a multinomial experiment, um, which is to say that there's a fixed number of identical independent trials, and each outcome of the trial can be classified into several different categories, one of several categories, and the probability remains constant for each trial, so which is they're independent. Um, For a multinomial experiment, the chi-square test evaluates how good the sample distribution and theoretical distribution fit. So let's say we want to test whether or not a die is loaded, um, which is to say, do we want to know if the theoretical distribution of rolls, which is, each side has an equal likelihood of showing up, matches the experimental one. If it's loaded, it's going to land on one number more than the others. So we record the outcomes of rolling a test die 100 times and compare to what we would expect for a fair die. So as I mentioned, we expect that each number would show up about 1/6 of the time, so roughly equivalent. So the expected value could be calculated as number of trials times probability for each trial. So 1/6 is approximately 17. So we'd expect to see approximately 17 of every number in that 100 rolls if the die is fair. Um, so let's say these are the frequency distribution from our experiment. We've got only 8 threes and 25 fives. That's 17. That's fairly close to 17. That's fairly close. That's maybe close, and but these two, just looking at it, seem kind of questionable. So is that far enough off to say the die is not fair? So we'll use a hypothesis test with the chi-square test statistic. For goodness of fit, our hypotheses are, the null hypothesis is that our observations match what we expect to see in theory. The alternative is that they don't match. So since the null hypothesis always contains equality, the assumption is the data values are equal to the theoretical distribution for null. In this case, the probabilities for the various outcomes are all the same. I've got a 1 in 6 chance of rolling a 1, a 2, a 3, whatever. So since they're all the same, I can phrase my null hypothesis as probability of outcome 1 is equal to the probability of outcome 2 is equal to the probability of outcome on to however many outcomes I have. The alternative is there's some difference in the probabilities. So we could phrase these as such. P1 equals 1/6, P2 equals whatever. If these were different, I could phrase it as, P1 equals, maybe I've got a die with two ones and no fives. So I've got 2/6 of rolling a one, some whatever the probabilities are. The alternative, again, is there's some differences. K here is important to note. This is the number of possible outcomes. So if I'm got a 6-sided die, it's 6. If I've got a deck of cards, it might be 52. It might be 4 if I'm looking at queens or kings or something like that. It's 4 if I'm looking at suits. 13 if I'm looking at individual card types that like kings or queens. It's however many possible outcomes I have. Again, as we learned before, the sum of probabilities of all the outcomes is equal to 1 each time. All right, so for our die rolling example, there should be the same probability for each outcome, so they should all be equal. All right, so let's talk about the test statistic. So we're going to look at the difference between observed frequencies and expected frequencies. Like with what we learned for calculating standard deviations, if we just add up all the differences, it's going to cancel out and we'll end up with the sum of 0. So sometimes we've also got to account for the fact that sometimes we have different probabilities for different outcomes. So we're going to do the same thing we did with calculating standard deviations and square the differences between observed and expected frequencies, and then going to divide the squared difference by the expected frequency. So it's kind of like doing a standard deviation calculation. It's kind of conceptually similar. We're going to just assume that everything we're talking about here meets the requirements of a multinomial experiment, because we're not going into depth on what that means and what that takes. We're just going to assume everything, all the questions in this section meet that. We do have some other conditions to have to meet. As before, we need to randomly selected sample data. We need calculations that use frequency counts for each category, and we need an expected frequency for each category of at least 5. So I need to do enough experiments that I would expect to get at least 5 in each category. I should not have a value of less than 5 in any category, or I should not expect a value of less than 5. So if I was doing experiments where my expected probability was 1 in 10 for one thing, I would need to make sure I did enough. 1 in 10. I would need to do at least 50 experiments, because then I could reasonably expect at least 5 values that met that. All right. So my chi-squared statistic in this case is going to be the sum of the observed frequency minus the expected frequency over the expected frequency, and square that difference, the sum for each possible outcome. Okay. If the observed values are quite a ways from the expected values and they're squared, that numerator is going to be large, and it's going to give us a very large value of chi-squared. So as the differences increase, so does the test statistic. How large is too large? It's going to, of course, be going back to those critical values as we talked about previously. We do have one addendum for finding the critical values. The degrees of freedom here is now possible outcomes minus 1, not sample size. It's possible outcomes we're after. So for our die example, if we're using a 6-sided die, we'd have 5 degrees of freedom. We've got 6 possible outcomes, so 5 degrees of freedom. right, we need the table with critical values, degrees of freedom. We compare the test statistic with the critical value. If the test statistic is larger, we can reject the null hypothesis. Okay, so let's look at a more practical example. We've got a bank that wants to evaluate its ATM use, and the manager assumes that the ATM is used consistently throughout the week, including weekends. She wants to do a 5% significance level test to test a customer's claim that the ATM is a lot busier on some days of the week than other days. So during a randomly selected week, the bank recorded the number of times the ATM was used each day. So they recorded every use for a whole week in just some random week. Okay, and here are their results. 38 on Monday, 33 on Tuesday, 41, 25, 22, 38, 45. That looks like some fairly large differences, possibly. But how large is actually significant? So, the probability, null and alternative hypotheses. The null hypothesis is that the proportion is the same for every day of the week. All right, proportion who use the ATM does not vary by day of the week. So you have a 1 in 7 chance. Proportion does vary by the day of the week. So we could write this as such. Tricky part might be calculating what that P should be. And I'm getting on a mental rabbit trail trying to think through that, but that's not the point right now. So what distribution do we need to use? And state the level of significance. So we're looking at observed values versus expected values. We're assuming the necessary conditions for this section, so chi-squared is going to be a good fit here. Level of significance given was 0.05. Okay. We need to first get the expected value for each day of the week. Since we're assuming that it does not vary each day, probability should be the same for every day. So we should calculate it as follows. So we could just add up the total number of customers that used it during the week and divide that by the number of days of the week. So 242 over 7. That would give us the estimated value. So it's just taking the number that actually did use the ATM and distributing that evenly over the week. So let's calculate the chi-squared. We've got 38. So expected value. Monday was 38. Tuesday was 33. Wednesday is after Tuesday. Okay, 41. Thursday is 25. You'll note that these values don't change. Because we're expecting the same use every day, those values don't change in this case. We get approximately 12.3. Okay, so degrees of freedom, we've got 7 days of the week, minus 1, so we've got 6 degrees of freedom. Alpha is 0.05, so looking at the table, which I do not have open next to me anymore, we get a 12.592. Okay, so what this looks like is our rejection region is up here. Past 12.592, our value is 12.314, so we cannot reject the null hypothesis. We're here in the fail to reject region. So there's not sufficient evidence to support the customer's argument that the ATM is used more often on whatever particular day of the week they try to go. Okay, so we can do this also in the TI-84 plus. So we've got an example with the fast food restaurant serving buffalo wings. The managers noticed that these are the trends they usually see for flavors. Looks like classic medium is their most popular. They want to run an ad campaign to promote some of their non-traditional specialty wings, and they want to know if that made an impact. So after 10 days, they get the following results for numbers sold. Okay. Is there sufficient evidence at the 0.05 level of significance to say the promotional campaign made any difference? All right. In this case, our proportions expected probabilities are different for each group. I'd expect that to be 20% of the total, that'd be 50, and these three to be 10. That's the expected null hypothesis, that the proportions are the same as they were before the promotional campaign. So to write this mathematically, we need those theoretical probabilities. We'll label them P1 through P5 in the order they were given. So spicy garlic was 20%, classic medium was 50, teriyaki, hot barbecue, and Asian were each 10. Have the following: 0.2, 0.5, 10, 10, 10. So we can state the null hypothesis as such, and the alternative as something's different. Okay, so since we're seeing whether things match the expected values, and we're assuming for this section that we meet all the requirements, we're going to use the chi-squared test. Level of significance given was 0.05. So let's gather the data and calculate the necessary statistics. So we need to calculate the expected value of the number of orders. So we had a total of 1,258 orders. If we multiply the expected probability times that number of orders, we should get expected values for each category. You'll note it says some TI-84 plus calculators can do this for goodness of fit. So if yours doesn't, I'm sorry. I have not gone in and looked at what the appropriate Excel functions are for this. I know the chi-squared test is built into Excel, so we should be able to do this in Excel, and I presume in Google Documents, or sorry, Google Sheets as well, but I have not tested that. So we can enter our data. They're putting the experimental values is in variable 1 and the expected values in variable 2 here. They're selecting the goodness of fit test, GOF for goodness of fit. We'll calculate, it will prompt you for observed, expected, and degrees of freedom. So we give it the first variable is observed, the second is expected, and 4 degrees of freedom. We've got 5 categories, so 5 minus 1 is 4 degrees of freedom. Select calculate, and it will tell us the chi-squared value, the p-value associated with that. So as we talked about in the hypothesis testing we covered last week, the p-value is the probability that would be associated with the t statistic or z statistic. In this case, it's the probability associated with this chi-squared value. So if I had a table that had a column for 0.566 and 4 degrees of freedom, that would be the chi-squared value. So if, as we saw with the previous examples in last week, if this p-value is less than my level of significance, then I can reject the null hypothesis. Since it's greater than that, I cannot reject the null hypothesis. So chi-squared is... Did I miss something? 2.94. Okay, they've got the decimal place misplaced here. It should be 2.95, not 2950 point and. So please note the typo here. P-value is 0.5662. The level of significance was 0.05. Since the p-value is not less than the level of significance, we failed to reject the null hypothesis. So our ad campaign was not effective in promoting changing that proportion of wings being sold. Okay.